Welcome back to the deep dive. Today, we're jumping into something pretty exciting in AI.
Yeah. What have we got?
We're looking at how large language models,
Yeah.
LLMs, and also the multimodal ones, LMMs.
Right, the ones that handle images and stuff too.
Exactly. How they're getting pushed beyond just, processing info to actually reasoning about it.
Ah, okay. Yeah, that's a big area. We've definitely seen some impressive strides there recently.
Like what?
Well, think about models like OpenAI's O1 or DeepSeek R1. They're tackling really complex math problems, generating pretty sophisticated code.
Tasks that need actual logic, step-by-step thinking.
Precisely. And often the key is this thing called chain of thought reasoning.
Okay.
CoT chain of thought. Let's unpack that a bit. So instead of just spitting out an answer,
Right.
the model kind of shows its work, breaks the problem down into smaller steps.
That's a good way to put it, yeah. It builds a sequence, a chain of intermediate reasoning steps.
Like solving a puzzle piece by piece. Exactly. And this methodical way of doing things, it seems to really boost the accuracy of the final output.
Especially for text-based tasks, I gather. Math, code.
Yeah, definitely seen huge gains there. But what's really interesting now is seeing this strategy, CoT, moving into the visual domain.
With those LMMs we mentioned, the ones that see images.
Exactly. These advanced LMMs can process images and text together, so they can do things like visual understanding, but potentially with more structure, more reasoning.
Analyzing a scene, step by step, maybe, instead of to the glance.
Something like that, yeah. It's moving towards a more considered analysis.
Makes sense. Now, what about the other way around? Not understanding images, but creating them.
Good question. There has been some early work looking at CoT-like ideas for text-to-image generation.
The autoregressive kind, where it builds the image piece by piece.
Yeah, that paper, Image Generation with CoTs, sort of framed that progressive generation of image tokens, like little patches of the image,
Right.
as a form of CoT.
So each new patch depends on the last one, like steps in a text argument.
Kind of, yeah. It focused on optimizing that sequence to get a better final picture. But the research we're digging into today takes it, well, quite a bit further.
How so?
It introduces a really novel approach that enhances CoT specifically for making images from text. It's quite clever, actually.
Okay, you've got my attention. Let's get into the technical side. What's the core challenge they're addressing?
Well, the thing with image generation compared to just understanding an image is it's way more complex in some ways.
How do you mean?
You're not just identifying things. You have to interpret the text prompt, figure out this cross-modal alignment, how words map to visuals, and then synthesize all these tiny, fine-grained visual details.
Right, you're not just seeing the scene, you're painting it from scratch based on instructions.
Exactly. And getting all those details right, making them coherent. That's tough.
So how does CoT help with that?
So the researchers proposed this idea of dual-level SOTI reasoning specifically for image generation. 2 layers of thinking, basically.
Dual level. Okay, what are the 2 levels?
The first one they call semantic-level CoT. This is all about textual reasoning that happens before any pixels get generated.
Before drawing starts, what's it reasoning about?
It's high-level planning, thinking through the prompt. What objects should be there? What should they look like, their appearance? Roughly, where should they be positioned in the scene?
So it's like writing a little text description, a plan for the image first.
That's a perfect analogy. It's designing the global structure, the blueprint, using text.
Okay, can you give an example? How does this help?
Yeah, figure 2 in the paper has some good ones. Imagine the prompt is a flower cultivated in the country where Amsterdam is located.
Okay, Netherlands. So tulips.
Exactly. The semantic level CoT can reason. Amsterdam cherry, Netherlands tulip. So it plans for a tulip. Without that step, the baseline model they use, Janus Pro, might just draw any old flower.
I see. It connects the dots, uses world knowledge before generating.
Right. Another example they give is a pig on the bottom of a train.
That's an unusual image.
It is. And the semantic reasoning figures, okay, a pig there isn't likely to be standing up normally. It's probably lying down.
Which makes the final image much more plausible, even if the scenario is weird.
Correct. It avoids just literally sticking a standing pig under a train. And this whole planning phase, this semantic CoT, it's just a sequence of text tokens.
Okay, so that's the high-level text plan. What's the second level?
The second level is token-level SIOT. This relates more closely to that earlier idea. It's about the actual patch-by-patch generation process of the image itself.
The step-by-step drawing part.
Exactly. Each new image token, each little patch, is generated conditioned on the image tokens that came before it.
So ensuring consistency as the image builds up.
Precisely. Token-level CoT is focused on the low-level details, generating the right pixels, making sure adjacent patches connect smoothly, maintaining that visual coherence across the image.
So semantic is the what and where plan in text, and token is the how to draw its execution in image patches.
You got it. One's a sequence of text tokens planning the image, the other's a sequence of image tokens building the image.
Okay, cool concept. But how do you actually get a model to do this and optimize both levels together?
Right, that's the trick. They introduced a new framework called BiCoT-GRPO.
BiCoT for the two levels, I guess. What's GRPO?
BiCoT, yeah, for the dual chain of thought. GRPO stands for Group Relative Policy Optimization. It's a type of reinforcement learning framework.
Reinforcement learning. So training with rewards.
Basically, yes. Teaching the model through trial and error, rewarding it when it does things well according to certain criteria. This framework is designed to jointly optimize both the semantic planning and the token-level generation.
Okay, how does the generation process actually work within this BiCoT GRPO thing? Is it sequential?
Yeah, it's essentially a two-step process. Figure 3 in the paper shows it nicely. First step, based on your input prompt.
Like a pig on a train.
Right. The model first generates the semantic-level CoT, that text plan we talked about,
Good.
reasoning about the pig probably lying down, etc.
Okay, step 1, generate the plan.
Step 2, the model then generates the actual image tokens, patch by patch. But here's the key part. It's conditioned on both the original prompt and that semantic CoT plan it just created.
Ah, so the plan directly guides the drawing process.
Exactly. And they mention using a special token like imstart, especially in these unified LMMs or ULMs like Janus Pro.
Unified, meaning they handle text and images together smoothly.
Yeah, these models are built for that. So the start token signals, okay, stop the text planning, start generating the image tokens now using the plan.
So it really integrates the understanding part of the LMM directly into the generation.
Precisely. It uses the ULM's ability to understand the prompt to inform the semantic plan, and then uses both the prompt and the plan to guide the detailed image creation.
And that GRPO reinforcement learning part helps tune this whole two-step dance.
Yeah, the paper mentions GRPO helps train the model to make better choices during this process, essentially reasoning twice. Once for the plan, once for the image within a single generation flow. It involves some clever comparison mechanisms during training.
Okay, that makes sense. But training with reinforcement learning needs rewards. How do you reward an image? Beauty is subjective.
Right, that is a huge challenge. You can't just say correct or incorrect like with math. So they went beyond simple rules and created an ensemble of vision experts to provide the reward signal.
An ensemble, like a panel of judges.
Kind of. Figure 4 shows this. It's a combination of different specialized models, each evaluating the generated image from a different angle.
Interesting. Who's on this panel?
First up, you have human preference models, or HPMs. Think models like HPS or image reward.
What do they do?
They're trained on tons of data about which images humans prefer. So they assess the overall aesthetic quality, but also how well the image matches the prompt.
Yeah.
They give a sort of holistic score, RHPM.
Okay, captures the looks good and relevant aspect. Who else?
Then there's an object detector. They use open vocabulary ones like Grounding Dino or YOLO World, which can find lots of different objects.
So checking if the things mentioned in the prompt are actually in the image.
Exactly that. And also their spatial relationships. Is the pig under the train? Are there the right number of objects? This gives object existence rewards, or DET, and spatial rewards, are spatial.
More factual checks. Got it.
Next is a visual question answering model, a VQA model, like BLIP or GIT.
How does that help reward image generation?
They reformat parts of the prompt into questions. If the prompt was a blue car next to a red house, they might ask the VQA model, is there a blue car, and is there a red house? The model's confidence in answering yes becomes a reward score, RVQA. It checks existence and attributes.
Clever. Verifying specific details through questions. Is there a fourth judge?
Yep. The final one is an output reward model, or RM. Here, they used a fine-tuned LLV1 vision model.
What's its job?
This one looks at the overall alignment between the entire prompt and the generated image. Does the image, as a whole, capture the meaning of the prompt? It gives a sort of yes-no judgment, providing the RORM reward.
Wow, that's a comprehensive set of evaluations. HPM for aesthetics and relevance, detector for objects and layout, VQA for attributes, ORM for overall alignment.
Exactly. And the final reward signal used for training the generator.
Is just the average of all those scores.
That's right. They found averaging them acts like a regularizer. It stops the model from over-optimizing on just one thing, like making pretty pictures that ignore the prompt, and pushes for balanced improvement across the board.
Okay, so we have the dual-level CoT concept, the BiCoT-GRPO framework to implement it, and this ensemble reward system to guide the training. How did the final model, T2I-R1 they called it, actually perform?
The results look really strong, actually. They tested it on standard benchmarks, T2I Comp Bench, which tests compositionality.
Like putting different elements together correctly.
Yeah, attribute binding, spatial relations, object counts, and also on WISE, which tests using world knowledge.
And two, how did T2I-R1 do?
Significant improvements over the baseline model, Janus Pro 7b. On T2I Comp Bench, an average jump of about 13%. On WISE, even better, around 19% average improvement. Tables 1 and 2 in the paper have all the numbers.
Those are pretty big gains. Any specific areas where it excelled?
On T2I Comp Bench, the biggest gains were in attribute binding, associating properties like color correctly with objects. That went up by 19% on average.
So that semantic planning really helps get the details right.
Seems like it. On WISE, the improvements were a bit more spread out across the different categories.
How does it stack up against, say, the big diffusion models that are state-of-the-art right now?
That's the really interesting part. They compared it to models like FLUX.1, and T2I-R1 achieved comparable or sometimes better performance on these benchmarks.
Really? An autoregressive model keeping up with top diffusion models?
Yep. On T2I Comp Bench, it actually let in several subtasks, especially the spatial reasoning one. And compared to other autoregressive models, T2I-R1 was consistently the leader across both benchmarks.
That's impressive. What do the researchers think explains this strong performance?
They suggest that T2I Comp Bench boost comes mainly from the semantic-level CoT's planning ability, handling those complex compositions better.
Right, the blueprint helps structure things.
And the WISE benchmark improvements likely come from that semantic CoT helping reason about user intent and using world knowledge more effectively. But they also stress that the token-level CoT is crucial for actually generating a faithful, visually appealing image based on that plan.
So both levels are pulling their weight.
Definitely. Figure 5 has some examples showing failures when you take away one level or the other. It makes the importance of both quite clear visually.
They also messed around with the reward system itself, didn't they? Tried different combinations of those experts.
They did, yeah. Table 3 shows that. It confirmed that different reward models have different strengths. HPM was good for attribute binding. The object detector, unsurprisingly, was key for object existence. VQA also helped with attributes. The ORM seemed best at checking object relationships.
So no single perfect judge.
Pretty much. But they found that combining them worked really well. HPM plus the object detector was a good combo. Adding VQA on top of that, HPM plus detector plus VQA, gave really balanced, strong results overall.
And did using these combined rewards actually make the pictures look better to humans?
They did a human study just on visual quality. And yes, the results indicated that using these ensemble rewards, especially that HPM plus detector plus VQA mix, led to images that people rated as having better visual appeal.
Probably because of that regularization effect you mentioned, not optimizing for just one narrow metric.
Exactly. It encourages a more holistic quality.
Okay, let's wrap this up. What's the big takeaway here? The core innovation.
I think the main thing is T2I-R1 being really the first text-to-image model that explicitly builds in reasoning at two distinct levels, semantic planning and token-level execution, using this chain of thought idea.
This dual-level CAT.
Right. And the technical approach, identifying these two levels and then building the BiCoT-GRPO framework within a unified model to make it work, that's the key technical contribution.
And the results show it pays off. Big improvements, competing with top models.
Yeah, significant gains on benchmarks, strong performance against diffusion models in some areas, and clear leadership among autoregressive models.
Plus, the qualitative benefits, better understanding of complex prompts, handling weird scenarios better.
Exactly. It suggests this reasoning-first approach could be a really important direction for generative AI, making models that don't just generate, but actually think about what they're generating.
It definitely feels like a step towards more intelligent image creation.
Yeah.
Really fascinating stuff.
Agreed.
Well, for everyone listening, if you want to dive even deeper into the technical side, the research paper link is in the show notes, https://arcciv.org, PDF 2505, but 0000703V1. Definitely worth a read. Thanks so much for breaking all that down.
My pleasure. It was fun to discuss.
And thank you all for joining us on the deep dive. We'll catch you on the next one.